Let's talk about graphing quadratic equations. A quadratic function is a second degree function, which means the largest exponent is a 2. The biggest exponent tells you the degree of a polynomial. So it could be frequently, most often, in the form of f of x equals ax squared plus bx plus c. The most basic possible quadratic function is going to be just plain old f of x equals x squared. And if we look at a couple of the points that would be on this, let's say we go from 3 down through the integers to -3. Well, the y values are going to be each of these squared. So that becomes 9, 4, 1, 0, 1, 4, 9. I'm just squaring the x values, for instance, on a graph like this. Then graphing those points will give us the point 1, 1. Now, notice on this, they're using a different scale along the x-axis than they do along the y-axis. So here they're counting by 1s, here they're counting by 2s. So the point 0, 0 is going to be right here. 1, 1 would be here. 2, 4 is over here. 3, 9 would be up here. -1, 1, -2, 4. So this is your standard graph of just y equals x squared or f of x equals x squared. Now, if we look at the graph of y equals 2x squared, recall from the stretching and shrinking characteristics that if you multiply your function by a positive number, as long as that number is on the outside of the function. For instance, if we want to look at f of x equals 2x squared, then this is going to be stretched away from the x-axis by a factor of 2. And the graph actually looks like this, the green one. So this now has each point, it still has 0, 0. But instead of 1, 1, it now has 1, 2. Instead of 2, 4, it now has 2, 8, doubling each of the y values. We can go farther and look at the graph of y equals 3x squared. So that it has 0, 0, and then 1, 3, and 2, 12. That doesn't even fit on here. But you see what's going on. So each time, this first point actually goes when you go over 1. If it's a 1x squared, it goes up 1 unit. If it's a 2x squared, it goes up 2 units. If it's 3x squared, it goes up 3 units. Because when you plug in 1, 1 squared is still 1. And 1 times whatever your a is, we could look at this as ax squared, right? Plus bx plus c. So the next point 1 unit over from the vertex will go up whatever a is. We can look at the graph of 1/2 x squared, and now it only goes up halfway to 1. And sure enough, the first point is actually right here at 1, 1/2. This is the point 1, 1. This is the point 1, 2, 1, 3. And again, that only works because 1 squared is still 1. So 2 times 1 squared is just 2 times 1. So it's 2. If we plug in a negative value, that's going to give us a reflection over the x value, over the x-axis. So the graph of y equals negative x squared is a perfect reflection of the graph of y equals a positive x squared across the x-axis. Now let's do away with some of these and take a look at what other reflections and, well, we took care of reflections and stretching and shrinking. Let's look at other translations. For instance, let's look at the graph of y equals x squared back. Let's look at the graph of y equals x minus 2 squared plus 4. So here is our y equals x squared. This is the graph of y equals x minus 2 squared plus 4. So if you recall from your translations, this minus 2 should move it 2 units to the right. And the plus 4 should move it 2 units up. A plus 4 is going to move it up 2 units. It's on the outside of the parentheses. The minus 2 is going to move it 2 units horizontally, and anything that's in the parentheses goes horizontally instead of vertically and backwards from what you would think. So the minus 2, instead of moving it 2 in the negative direction, moves it 2 in the positive direction. Now, otherwise, it is a perfect replica of the y equals x squared, in that here we go over 1, up 1. Here we go over 1, up 1. And then if you go up 1 more, it goes up 3. If you go up over 1 more, it goes up 3. This can be written as f of x equals a times x minus h squared plus k. Now, because a minus h will move it h units to the right, and a plus h would actually move it h units to the left. So this moves every single point, in this case, 2 units to the right, 4 up. So the vertex is moved 2 units to the right and 2, 4 up. This point goes 2 units to the right, and remember, and we're counting by 2's going up, so 1, 2, 3, 4 units up. So the vertex, this turnaround point, the vertex of any quadratic equation written in this form is going to be at the point h, because it'll be the opposite direction for the h, for the inside, and then k. Change the first sign, keep the next. This graph also has a minimum point. The minimum point is the vertex, because the vertex is going to be the lowest point on the graph if the graph opens up. So the minimum point is also HK, depending on your particular book and your particular teacher. Sometimes they will say that the minimum value is K, and it occurs when X is equal to H. By the minimum value, they are automatically referring to the Y value, because there is no minimum X value. The domain of a quadratic function is always all real numbers, so negative infinity to infinity. The range is tightly related to the vertex and the minimum, or if it's going down, the maximum. So the range here for this function is from 0 to infinity. The range for this function, remember we're talking about the y values when we're talking about the range, goes from 4 to infinity. So the range, if it goes up, and if a is positive, greater than 0 is algebra for positive. If a is positive, then the range goes from k to infinity, because the graph is opening up. If A is less than 0, which is exactly the same as if A is a negative number, then the range is from negative infinity to K.